We have also found the variance. Variance of xj is nothing but sigma xj whole square. Generally, we'll represent variance as sigma square. Okay, but here since we are finding for xj, I have also represented xj. So sigma square xj is equal to variance of xj, which is equal to variance of xj. Xj is nothing but Sij plus Wj. Okay, so variance of Sij plus variance of Wj, and variance of Sij will be equal to 0. The reason behind that is the variance will tell you how it is changing, but here this is the constant value which will not change, so it is 0, plus variance of Wj is nothing but n naught by 2. Okay, so since variance of Wj is n naught by 2, I have represented that there. So now sigma xj whole square is nothing but 0 plus n naught by 2, which is nothing but sigma xj whole square is nothing but n naught by 2. This is nothing but the variance of xj. Okay, so this is what they'll ask you to prove in the exam. So in that case, you need to completely write until here. And sometimes in the question itself, they will also ask, show that the xj is uncorrelated. Uncorrelated in the sense xj is nothing but, what is xj? Xj is nothing but it is a set of x1, x2, so on, xn. Okay, so they'll ask you that you show that they are uncorrelated in the sense x1, x2, all these are independent, linearly independent, they are not depending on each other. So that is what they'll ask you to prove. Okay, so in order to prove that they are uncorrelated, I will just take xk and xj as two variables. Okay, from the set, whatever xj set I have, it is nothing but x1, x2, so on, xn, right? So in this set only, I'm just denoting it as xj and xk, and where j and k are not same. Okay, so in order to show that they are uncorrelated, we'll be using the covariance. We will be finding the covariance, because covariance will tell us how they both signals are varying with each other, changing with each other. Okay, so that is a reason, like I've taken covariance of xj xk, which is nothing but expectation of xj minus mu xj. This is a formula. Okay, so this is a formula we have, you need to remember this. Okay, remember. Okay, if you people recall your random process which you have studied, we would have written the same equation. So if you want to find the covariance, then the random variables, from the random variables you need to subtract the mean and take the expectation of that. Okay, but here since xj, you know that what is mu xj? Mu xj is nothing but mean value. See, this mu indicates mean value, mu x k indicates mean value. This also mean value, this also mean value, but this is a mean value of xj and this is a mean value of xk. Okay, so mean value of xj is nothing but Sij, and mean value of xk is nothing but Sak. One second. Okay, fine. So the mean values of xj and xk I'm substituting here. Okay, and again you know that xj is nothing but Sij plus Wj. Okay, but Sij, take this Sij to the other side, it will become xj minus Sij. So this entire thing can be replaced as Wj in this equation. So Wj, and this also xk minus Sik can be replaced with Wk. Okay, so that is what I have done. Okay, and you know that Wj, Wj we have assigned. Who is that? Okay, Wj we have assigned for this equation. So I have just taken back the same equation. Wj is nothing but integral 0 to t w of t pi j of t dt. Okay, so Wj, I am retrieving the same equation. Okay, where is that? Wj. The Wj is equal to integral 0 to t w of t into phi j of t. That is for Wj. And in the same way, I need to find Wk also. Okay, so Wk I am taking it as w of u phi k of u du. Okay, since j and k are not same, I've replaced the variable as u here. That's it. Okay, so covariance of xj xk, this equations have substituted in this equation. Okay, in this equation I've substituted this one and this one in this equation. So I've got as expectation of integral 0 to t w of t pi j of t dt. Okay, where I into integral 0 to t w of t pi w of u pi k of u du. Okay, so this is what I've got. Okay, now after this what I've done, I have rearranged everything, because you know that expectation, all the mean value will be found by found for the random variables. Okay, so here the random variables are w of t and w of u. Okay, so that is the reason what I've done, I have rearranged everything here. Okay, covariance of, just write it again, covariance of xj xk is equal to integral t is equal to 0 to t integral u is equal to 0 to t pi j of t pi k of u expectation of w of t into w of u dt du. Okay, and from the definition of correlation, we know that expectation of w of t and w of u is nothing but it is a correlation function. Okay, so correlation function, so I can represent this entire thing as rw of t comma u. Rw of t comma u, this entire thing I can just replace with Rw of t comma u, because whenever you want to find the autocorrelation function, we'll be using this formula itself. Okay, this is how we find the, see, as I've told you, mean how we find the mean expectation of, if I want to find the mean of x, I'll take as expectation of x. In the same way, if I want to find the autocorrelation function between w of t and w of u, I'll be finding using expectation of w of t into w of u. Okay, so this is how we find. Okay, this is the definition of autocorrelation again. So what I'll do, I'll replace this entire thing with rw of t comma u. Okay, so covariance of xj xk is equal to integral t is equal to 0 to t integral u is equal to 0 to t phi j of t into phi k of u into rw of t comma u, rw of t comma u dt du. Okay, so hope you are following. Hope you are following.
Yes, ma'am.
Okay, so now as I've already mentioned, this noise this noise signal is a stationary signal. Okay, stationary signal in the sense like its characteristics will not change. Okay, so since its characteristics are not changing, what will happen here is this autocorrelation function, it will not depend on t or on u. Okay, it will not depend on, see, this w of t and w of t are like the same white noise which is taken at time t and at time u. Okay, so it will not depend just on time t and time u, but it will depend on the difference. Okay, so because of this we can write rw of t minus u as rw of rw of t comma u as stationary process. Since it is a stationary process, we can represent rw of t comma u as rw of t minus u. It means that the autocorrelation function will not depend on t or u, but it will depend on the difference between these time intervals. Okay, so that is the reason we can write this rw of t comma u as rw of t minus u. Okay, now we need to find what is this rw of t minus u. Okay, so you know that the power spectral density, okay, power spectral density of the noise signal, you know, as it is nothing but m naught by 2, and you know the relationship between the autocorrelation function and the power spectral density. Okay, can anybody tell me the relationship between autocorrelation function and the power spectral density? Anybody knows this? I've already mentioned in some derivation. I've told you the relationship between autocorrelation function and the power spectral density. Anybody remembers? Anybody remembers? Anybody remembers? Bhavna? Bhavna,
Yes, ma'am.
do you remember the relationship between autocorrelation function and the power spectral density? General relationship. I don't want you to say here general relationship. No? Do you know or not? Okay,
No, ma'am.
fine. Okay, fine. I will only tell you Rx of t. Okay, it is nothing but the autocorrelation function. Autocorrelation function and the power spectral density. Okay, power spectral PSG forms a Fourier transform pairs. Okay, so if you want to find when you find the Fourier transform of Rx of t, you'll get power spectral density. When you want to find the power spectral density, you need to take the Fourier transform of Rx of t. Okay, if you want to find the autocorrelation function, then you need to take the inverse Fourier transform of power spectral density. Okay, so from this relationship, see, we already know Sx of f is nothing but n naught by 2. Okay, n naught by 2. Okay, so in the same way, if you find Rw of t for this Sx of f, you'll get as n naught by 2 only. Okay, n naught by 2 only. Okay, since you're getting sorry, you'll not get n naught by 2, you'll get as n naught by 2 into delta of t. Okay, see, you already know Sx of f, which is nothing but n naught by 2. Okay, the power spectral density of white Gaussian noise, you already know it as n naught by 2. Okay, it is nothing but for the white Gaussian noise is W of f. It is not Sx of f, it is SW of f for the white Gaussian noise W. For W, we are finding we know that its power spectral density is n naught by 2. Okay, so when you know this power spectral density of your of your white Gaussian noise, then you need to find the autocorrelation function. So take inverse Fourier transform so that you'll get autocorrelation function as n naught by 2 delta of t. Okay, this is how we find this Rw of t. But we don't want Rw of t, but we want Rw of t minus u. Okay, so wherever you have t, replace with t minus u. So n naught by 2 delta of t minus u. Okay, so this I'll name as some equation 4, I think so. I don't know. So first what we need to do, we need to replace Rw with t comma Rw of t comma u as Rw of t minus u, because since it is a stationary random process, okay, it will not depend on the time alone, time t or time u, but it will depend on its difference. That is the reason we'll be able to write Rw of t comma u is equal to Rw of t minus u. Again, I'm trying to find what is Rw of t minus u. Since we know that the white Gaussian noise has the power spectral density of n naught by 2, we will be able to find its autocorrelation function by taking inverse Fourier transform of this. Okay, when you take inverse Fourier transform of that, you'll get n naught by 2 into delta of t. Delta of t will get as delta of t. Okay, but I don't want Rw of t, just the time t, but I want the difference t minus u. So replace t with t minus u. So Rw of t minus u is nothing but n naught by 2 delta of t minus u, which is nothing but Rw of t comma u. Okay, so this I'll substitute this equation 5, I'll substitute in 4. Okay, substitute equation 5 in 4. Okay, so that your covariance of xj xk will be equal to integral 0 to t, this is for t, integral u is equal to 0 to t phi j of t into phi k of t Rw of t minus u, right? See the equation. You have Rw of t comma u. Rw of t comma u can be replaced with this one. Now n naught by 2 delta of t minus u. That's all. T minus u, dt and du, dt du, dt du. Okay. So this can be rearranged as See, anyway, this phi j of t, this is a function of only t, right? So I'll rearrange everything now. T is equal to 0 to t. Phi j of t I'll write first, and then n naught by 2 is a constant. I'll take it outside, and this integral 0 to u is equal to 0 to t phi k of t into delta of t minus u du dt. Anybody have doubts until here? Anybody have doubts until here? Please ask me. Anybody has doubts until here?
No, ma'am.
Are you people understanding what I'm trying to say here? Here my goal is to prove that the xj and xk, okay, where xj and xk are nothing but from the set only, x1 x2 so on, xn are there, no? Okay, I am I want to show that these are all uncorrelated, they are not depending on each other, they are mutually exclusive events. That is what I need to prove here. Okay, so in order to prove that only I have taken the covariance function. Okay, after taking the covariance function, I've just I'm further doing the mathematical analysis. That's it. Okay, I'm just doing the mathematical analysis. Okay, otherwise nothing great I'm doing here. Only after until this step is like you need to apply the concept. Okay, after this it's all the mathematical analysis that we are doing. Okay, so can you all remember the shifting property of delta function? Delta function which is nothing but delta of t function. Shifting property, have you heard this property anytime? Delta function, which is nothing but the impulse function. These all you have studied in your signals and systems. Anybody remember this? Okay, fine. Integral f of x delta of x minus x naught dx can be represented as integral. Okay, integral f of x. Okay, here you are integrating with respect to x. Okay, f of x delta of x minus x naught into dx can be represented as f of x naught. Okay, so it means that if you multiply any function f of x with the delta of x minus x naught in the sense at x naught, you will have the delta function. When you multiply that and integrate it, you will just have the value which is there at f of n. Okay, I'll just show you. Let me consider this is my f of x signal. Okay, so let me consider I have somewhere here delta of delta function at x naught. Okay, delta function x naught. When you multiply, all other values will be equal to 0, and only here you will have the value. Okay, and here you are taking the integration area under that, so you will have the impulse function only at that particular place. Rest all it will be equal to 0. Okay, rest all it will be equal to 0. That is what here this shifting property says. Okay, so this is your shifting property. So I'll use the same property here. So here if you observe, I have this one I'll take. So integral 0 to t what is it, phi k of u delta of t minus u du. Okay, no, only this part I have taken now. Okay, only this portion I have taken. Okay, from this equation, this I'll name as equation 6. From equation 6 I have considered only that part to apply the shifting property. Okay, but if you observe, I have pi k of u in place of phi f of x, you have pi k of u, but in place of delta x minus x naught, you have t minus u. If I consider u as x, here I have x naught minus x. Okay, but I should have x minus x naught. Can anybody tell me whether delta function is a even function or odd function? Delta function is a even function or odd function? You people know what is even function and odd function, right? Okay, fine. So delta function is a even function. So delta of t minus u, I have taken minus common. So minus even function and odd function, in the sense x of minus t will be equal to x of t. If x of minus t is equal to minus x of t, we'll call it as even function. Okay. So here, since it is even function, I could write as delta of minus of u minus t as delta of u minus t du. Okay, now I'll apply the shifting property. So shifting property, according to the shifting property, if any signal is getting multiplied with delta of x minus x naught dx, then its value will be f of x naught. So here in place of x naught, you have t. Okay, this x naught is nothing but t. Okay, comparing this equation with this equation, this I'll name as a and this I'll name as b. Comparing these two equations, we have got this will be equal to phi k of t. Phi k of t. Okay, this I will substitute in the sixth equation. This I'll substitute in the sixth equation. Equation b, I'll substitute in the equation b. Substitute it in equation 6. So this is what the equation I have. This equation I have taken, and what I'm doing, I'm just applying shifting property, which I already know. Okay, so we know that shifting property, integral f of x delta of x minus x naught dx will be equal to f of x naught. Okay, in place of x naught, you have sorry, here it is u, not t. Here pi k of u. Here also pi k of u delta of t minus u. Okay, so in place of x, you have u, and in place of x naught, you have t. Okay, pi k of u. Okay, so now this entire thing can be replaced with phi k of t. So here covariance of xj xk will be equal to integral t is equal to 0 to t phi j of t Oh, n naught by 2 is also there. N naught by 2 phi j of t, and this entire thing is nothing but phi k of t by using the shifting property. So into phi k of t dt. Okay, so this is nothing but the covariance function we have got, and you know that these phi j, phi k are nothing but the orthonormal basis functions. Okay, so if j is functions, are you people understanding? See, phi j and phi k are multiplied, and integral we are integrating it. Okay, so what will happen if j is equal to k? If j is equal to k, it is nothing but the energy of the signal. So when j is equal to k, n naught by 2 into 1, which is nothing but n naught by 2. Okay, if j is not equal to k, you know that they are perpendicular to each other. So n naught by 2 into this you have proved in the exam also. Prove that. Oh, not this one. No, Hilbert transform. Okay, fine. So the orthonormal basis function, you know the condition on orthonormal basis function. Integral 0 to t phi j of t into phi k of t dt is equal to 1 if j is equal to k, and equal to 0 when j is not equal to k. The same thing I am substituting here. So when j is equal to k, this integration value is 1. So n naught by 2. When j is not equal to k, it will be n naught by 2 into 0, which is nothing but 0. So finally I can write as covariance of xj xk is equal to n naught by 2 if j is equal to k, and equal to 0 for j not equal to k. So this indicates that they are uncorrelated. Okay, so the xj and xk are uncorrelated. Since they are uncorrelated, and these are nothing but the this xj xk are nothing but the Gaussian random variables. It is not just the random variables, it is the Gaussian random variables, because xj xj is nothing but Sij plus Wj. Okay, Wj is nothing but it is due to the additive white Gaussian noise. Okay, so the noise itself is Gaussian. Okay, so that is the reason it is getting added. Xj will also be Gaussian random process. Okay, Gaussian random process, and from this final statement, when j is not equal to k, the covariance value is equal to 0. Okay, so this indicates that they are uncorrelated. Okay, since they are uncorrelated, they are statistically independent also. Okay, they're statistically independent, and they're uncorrelated also. Okay, so this shows that xj and xk are uncorrelated. Since they are uncorrelated, they are statistically independent. Statistically independent according to Gaussian random process. Is this clear? There are lots of equations, and along with the equations, you people should also have some basic concepts related to random process. Okay, because not too much is required. Okay, so mean, variance, power spectral density, autocorrelation, then comes the probability density function. All these very few concepts are required. So what you can do is, even if you are not able to recall them right now, what you can do, you can make a note of all the headings. Okay, headings in random process. Those are nothing but the mean, variance, correlation, covariance, then power spectral density, probability distribution function, probability density function, conditional probability, all these very basics. Okay, if you can just go through all this, no, you will understand this topics thoroughly. Okay. Otherwise, when I am telling only, like, you can just follow. But wherever the equation comes and that equations are like derived from the random process, you can just mention there as remember, so that you'll be able to when you are studying also, you'll be able to think that okay, these are all taken from the random process and you need to remember them. Okay, fine. So so when they ask you in the exam about the prove that the correlator outputs are statistically independent, then you need to prove until here. Okay, and next what I'm teaching you, it is just the extension of this, but here you need not write, but it will be helpful for you for the next topic. Okay, hope you people are following. It's not so easy also. I know that because I'm using the random process concepts. So that's why I'm telling you, you can just go through your random process few topics which I've mentioned. Okay. Are you all following, listening to me? Are you all able to hear me?
Yes, ma'am.
Are you understanding what I'm teaching?
Yes, ma'am.
Yes, ma'am.
Yes, that's what, see, wherever I've substituted the equation, that there you might be feeling little difficult, I know. So only I'm telling you, you can just go back and check the random process concepts. That's just the basic equations there. Whatever I have used, whatever equations I've used here, you can just go back and check is that the same equation or not. Okay, Fine. Okay, fine. So as I've already mentioned, we will just give some extension of this topic so that it will be helpful for us in the next topic. Okay. So here, what I'm saying that the correlated outputs are nothing but x. Okay, x is nothing but x1, x2, so on, xn. Okay. So all these are statistically independent. Independent in the sense the output of one will not affect the other. Okay, if you can just recall conditional probability, if probability of B given A, okay, if they are statistically independent, you can just write as probability of B. Okay, so this is what it states. Okay, so instead of writing in terms of probability, here what we'll do, we will write in terms of conditional probability density function. Okay, using this we'll just represent the equation. Okay, so all this vector x is uncorrelated, therefore statistically independent. Since this is statistically independent, we can find the conditional probability density function of the correlator output x, okay, which is given as f x. Capital F indicates it is a probability distribution function. Okay, difference of probability difference of when you will generally write it in this way, fx of x. Okay, this is the probability distribution function. Okay, this will tell us how the probability is distributed throughout. Okay, throughout the experiment, that will be given by fx of x. But when it comes to the probability density function, pdf, small pdf, it is nothing but it is denoted as fx of x. Okay, which is given as d by dx of fx of x. It means that here we are finding the difference. Okay, so where this x is a vector space and this is a sample of this x. Okay, so fx of x can be represented as d by dx of probability distribution function. Okay, so since the probability distribution function, since the correlator output x is statistically independent, since they are not depending on each other, we can find the overall probability, conditional probability density. Why I am going with the conditional probability? Because here what I am doing, I am sending mi. Okay, mi is a signal which is generated at the transmitter. Okay, so source is generating mi. Okay, mi, from mi I am converting it to si. Okay, si, from the si, by si will get added with w of t, and it will get added with w of t, and it will generate x of t. Okay, from this x of t I am taking xj. Okay, xj is nothing but the correlator outputs. Okay, so I need to find what is the condition probability when mi is sent, what is x that I'm going to receive. Okay, in order to find this, I'll be going with the conditional probability density function, which is given by fx. Okay, this is the capital X, fx of small x. Okay, this is again x given mi. Okay, given, whenever I will write it as given like this, this slash indicates given mi. It is said to be the condition. When mi is given, x is the received vector. Okay, so that will be found by taking the multiplication of all the vectors, conditional probability density function of this vectors, which is given by f x1, where this x1 is a sample of this x1, x2, xn, like that. So x1 mi only I'll write. Okay, into probability of probability density function, conditional probability density function of x2 given mi. Okay, so on like that, f xn given mi. Okay, so this is how we find the conditional probability density function of the vector x. Okay, So here it is nothing but the multiplication of all this conditional probability density functions. Okay, only if they are independent I will be able to write in this way. Okay, only if they are statistically independent, then only I will be able to write in this way. Okay, if they are dependent I will not be able to write in this way. Okay, only here the condition is we have already proved that they are statistically independent. Okay, since they are independent, then only I'll be able to take as to find the overall conditional probability. I can take the probability of individual probability density function of individual vector x1, x2, x3 like that. Okay, so this in short I can write as fx of x given mi is equal to phi. You know that phi indicates it is a multiplication. Phi is equal phi j is equal to summation indicates addition, pi indicates multiplication. Hope you all know this. So j is equal to 1 to n f x j, and these are nothing but the samples of this xj mi. Okay, so this entire thing I've just represented in the small equation. Okay, so this fx of x mi is there. No, this is said to be likelihood function. Likelihood function. Okay, it is said to be the likelihood function. Likelihood function. Likelihood function. Okay, so this conditional probability density function of the vector x is said to be the likelihood function. Using this likelihood function, we'll be able to decide whether which symbol is transmitted, whether m1 symbol is transmitted or m2 is transmitted or m3 is transmitted or mm is transmitted. Okay, so the receiver and what okay, next topic when I'll start, I'll give you the introduction there, but otherwise this is said to be the likelihood function. Okay, this is said to be the likelihood function. Okay, using this we'll make the decision which variable, which message has been transmitted. Okay, and here you know that this is nothing but the probability density function. Okay, and this probability density function is nothing but the probability Gaussian probability density function. Why it is Gaussian? Because the variable, whatever variables I have, x1, x2, xn, these are nothing but the Gaussian variables. Okay, so since these are Gaussian random variables, I can represent each one x j or x1. Okay, if it is x1, okay, x1, small x1 given mi is equal to, I can represent this as 1 by, see, you people know the equation of Gaussian process equation or Gaussian equation of this. Okay, if x of x is nothing but 1 by root of pi n naught. Okay, 1 by root of pi n naught exponential of minus 1 by n naught xj minus see, first I'll give you the equation of your Gaussian random process. From that I will be able to derive this, because directly if I write you may get confusion. Okay, so first what I'll do, I'll give you the equation for Gaussian variable. Okay, once again let me give you the equation for that. Generally the probability density function if x of x can be, for the Gaussian random process, can be represented as 1 by sigma root 2 pi. Okay, sigma, this sigma is nothing but the sigma square is variance, sigma is standard deviation. Okay, sigma root 2 pi and exponential of okay, e power minus x minus mu divided by 2 sigma square, this square. Okay, so this is the equation. Okay, but here in place of sigma I'm substituting sigma. So you know that sigma xj is nothing but n naught by 2. Sigma square xj is nothing but n naught by 2. Okay, if I want sigma, then I need to take square root, so it will become as 1 by root to 2 pi. This sigma, if I take inside, it will be sigma square. So it is nothing but n naught by 2 exponential minus x minus xj. Here x is nothing but xj minus mu. Mu of xj is nothing but Sij divided by 2 sigma square. 2 sigma is sigma square is nothing but n naught by 2. So this 2 will get cancelled. Here also this 2 and this 2 will get cancelled. So I'll be left out with pi by root of pi n naught exponential. This 1 minus 1 by n naught we have taken outside. So minus 1 by n naught xj minus Sij whole square. This is the probability density function of each one. Okay, so here I am specifically taking for 1. So this, it will be Sij. Have you understood this, how I got this equation? Have you understood? Anybody want me to repeat this? Anybody want me to repeat this? See, I'll just go back. See, if I want to find the conditional probability density function, I need to know the probability density function of each vector x1, x2, xn, like that. Okay, each vector values the probability density function I need to know. Okay, so in order to find that, what I'm doing, I have just considered the equation of Gaussian random process. I'll just write it again. Maybe here it is congested. I'll just write it again. You can just see. See, you understood that the x1, x2, whatever correlator outputs you are getting, they are Gaussian random variables. Since it is Gaussian random variables, you have the equation for Gaussian distribution, which is given by fx of x is equal to the equation to find the Gaussian distribution function. Okay, you know that the Gaussian distribution function will be in this way, right? Okay, the equation for this is given by 1 by sigma root of 2 pi. This is the equation, standard equation. 1 by sigma root of 2 pi exponential of minus x minus mu whole square divided by 2 sigma square. This is the equation of Gaussian distribution function. Okay, this is the equation for Gaussian distribution function. Here I need to find for f x1 of x1. Okay, and given mi. Mi is like this is a conditional probability. Okay, so the equation will remain same. 1 by see, you know that what is sigma xj square. Okay, instead of sigma I will take sigma xj. Okay, under root of 2 pi. Here also minus exponential minus x. X is nothing but x1 here. X1 minus mu. Mu is nothing but is, okay, I'll write as mu only. Mu of xj. One second. Minus x minus mu. Mu is nothing but here it is nothing but xj minus mu of xj I need to find. Okay, whole square divided by 2 sigma xj square. Okay, so this is what the equation. This is what the equation for x1, x1 or xj. Okay, so since it is xj, here also I'll have x1 here. Okay, but what is the sigma xj we have got? Sigma xj square we have got as n naught by 2. Okay, j, where j is equal to 1 to so on n. Okay, so here sigma x1 square will also be equal to n naught by 2. Okay, so that I will substitute here, and in the same way you got as mu xj is equal to Sij. This is what you have got. In the same way mu x1 will be equal to Si1. Okay, so that I need to substitute here. So f x1 given, this is just x1 given n mi is equal to 1 by sigma x1. I want sigma x1, so sigma x1 will be equal to, from this it will be root. Okay, so root 2 pi into root n naught by 2. Sigma x1 value is nothing but root n naught by 2. Exponential minus x1 minus mu xj. Mu xj is nothing but sij. Si1. J value is 1. Okay. Whole square divided by 2 into sigma xj square is xj or x1 square is nothing but n naught by 2. Okay, so this 2 and this 2 will get cancelled, so I can write as, and here also this 2 and this 2 will get cancelled, so it will be 1 by root pi n naught exponential of minus x1 minus si1 whole square divided by n naught, or I can write in the other way as minus 1 by n naught. You can take common. Okay, so the same equation is represented here. Okay, but instead of x1 x2 like that, here I will just take in general as xj. Okay, xj minus sij. Okay, so just compare this equation with that, it is the same one. Okay, sij, okay, xj. Okay, so now finally you've got your xij. Xj given in my is nothing but 1 by root pi n naught exponential, e or exponential. If I write exponential, then I have to write side to that, or e power minus 1 by n naught xj minus sij whole square. Okay, so this I'll substitute it in this log likelihood function. Okay, so it will be equal to f x of x given in my is nothing but phi j is equal to 1 to n 1 by root phi n naught exponential of minus 1 by n naught x j minus sij whole square. Okay, so now what I'll do, I'll substitute individually x1, x2, x3 like that. So it will be x given in my is equal to pi. So pi in the sense multiplication of each. When j is equal to 1 I'll take, when j is equal to 2 I'll take, when j is equal to 3 I'll take, like that I'll write. So 1 by root pi n naught e power when j is equal to 1 minus 1 by n naught x1 minus si1 whole square into 1 by root pi n naught exponential power minus 1 by n naught into x2 minus si2 whole square. Next, so on like that, 1 by root pi n naught exponential power minus 1 by n naught into n value, last value is n, so xn minus sin whole square. Okay, so if you observe 1 by pi n naught is repeating n times, so I can take it as 1 by root pi n naught whole power n, because it is, I'm getting it n times. Okay, so I can write as 1 by root pi n naught whole power n, and here you know that e power a into e power b into e power c can be represented as e power a plus b plus c, right? So the same formula I'll use here, a power m into a power n formula. So it will turn to exponential of all addition of all the exponential terms. So it will be minus 1 by n naught x1 minus si1 whole square minus 1 by n naught x2 minus si2 whole square, so on, minus 1 by n naught into xn minus sin whole square. Okay, so this can be represented as, this entire thing can be represented as 1 by root phi n naught whole power n e power minus 1 by n naught I can take common, so if I take common I'll be left out with x1 minus si1 whole square plus x2 minus si2 whole square, so on plus xn minus sin whole square. Okay, so this can further be represented as f x of x given in my is equal to 1 by root pi n naught whole power n exponential of minus 1 by n naught. Here what I'll do, I'll take summation j is equal to 1 to n xj minus sij whole square. Okay, this is what we can write. Or here I have in the denominator like this, I can write as fx of x given in my is nothing but pi n naught whole power minus n by 2. Okay, because this is nothing but root will be written as n by 2. Okay, this root can be represented as n by 2. Okay, if I take it to the numerator, it will be 5 n naught whole power minus n by 2 exponential minus 1 by n naught summation j is equal to 1 to n xj minus sij whole square. Okay, so this is the log likelihood, not log, likelihood function of the output vector x. Okay, output of the correlator function x. Okay, so as I mentioned, this is useful for your further next topics. Okay, otherwise this topic ends here, where we have proved that they both are uncorrelated. That's all with respect to this topic. They'll ask until here only. Okay, whatever analysis I have done after this, it is all helpful for us for the next topic. Okay, so this is very, very important for you to remember. Okay, rest all the analysis, it's okay, but this is what you need to remember, because based on this equation only will be proceeding further. Okay, and see, if you see this equation, okay, if you see this equation, see pi n naught, all these are constant, and even sij is also a constant. This is also known. Okay, the only unknown is xj. Okay, so this conditional probability density function is purely depending on this xj value. Okay, based on this xj, this value will change. Okay, based on this value, this xj only will be able to identify which symbol is transmitted. Either it is m1 or m2 or mm, whatever is transmitted, will be able to find out. Okay, so the sufficient sufficient condition here is to make any decision is xj. xj is a sufficient condition. Okay, so just by using xj, we'll be able to find out whether the symbol whatever is transmitted is m1 or m2 or mm, like that. Okay, hope this is clear to all of you. I have already passed you the notes. You just go through it. Okay, so you'll definitely understand. But there, no, what I did, I have not expanded all these equations like this. I have directly given this equation. Okay, I have not done all this, whatever explanation I've given you here. I didn't do it in the notes. Okay, otherwise, if you want, you can make a note of this. Otherwise, as I've already mentioned, this is the main equation which is required for us. Okay, this is the main equation which is required for us. Okay, this is the main equation which is required for us, and this is said to be the likelihood function. A likelihood function which we'll be using to make the decision in determining the symbol transmitted. Is this clear? Is this clear, ma? Is this clear?
Yes, ma'am.
That's what. See, in the next topic, I'll show you exactly how we'll be using this equation. You need to remember this equation. Remember this equation. Okay. Next. So, what is that we are doing until now? I'll just explain you. See, I'll just take back the what is that? The block diagram, which we have seen. Okay, from the transmitter to receiver, we'll see what we have done. Okay, so what is that? You'll have a message source. Okay, this message source, what it will do? It will emit the symbols mi. Okay, where I will be equal to 1 to m symbols. Okay, then from this symbol, what we'll do? See, I'll just continue the class until 11:20. Okay, because third hour again I've got a class. Okay, from 11 to 11:55 I've got a class. But since you people have Rubicon class, I'll not, I will not be taking, right? So what I'll do, I'll take until 11:20 and I'll leave you. Okay. So that you can take 10 minutes break, again joining, again leaving, joining, it is not correct. Okay, so that is the reason I'll leave you at 11:20 so that you can take a break of 10 minutes and you can join for your 11:30 Rubicon class. Okay. Is this clear what I'm telling you? I'll continue class until 11:20 and I'll leave you at 11:20 so that you can have 10 minutes break and you can join to your Rubicon class. Okay. Okay, fine. So here we'll just come back to the basic circuit diagram, block diagram, which we have seen already. Okay, so in the introduction class only I taught you this diagram. Where, so you'll have a message source in my it will emit mi symbols. Okay, then you'll give it to the vector transmitter, which will give you SI vector. Okay, where SI is nothing but SI1, SI2, so on like that, SIN. You'll get this vector. Then you'll give it to the modulator. Okay, modulator, where this modulator will have the carrier wave as well. Okay, so this entire thing, so here, this entire thing from here to here is nothing but the transmitter. Okay, so this modulator will give you SI of T signal. Okay, then this SI of T signal will be passed through the channel. Okay, it will be passed through the channel, where the channel will add the additive white Gaussian noise and it will give you X of T. Okay, so the detector, okay, you'll have the detector which will estimate or which will detect the transmitted signal. So you'll get X from this. Okay, once you get X from this, what will do, you'll give it to the vector decoder or vector receiver or decoder. What this vector decoder will do, based on this X value, okay, based on this X value, it will estimate the final transmitted bit. Okay, so estimate M cap. Okay, where this M cap should be almost equal to Mi. M cap should be almost equal to Mi or exactly equal to Mi. Okay, so detector will detect or it will convert the X of T to X, and based on this X, the vector decoder, what it will do, it will do the reverse operation from, see here what is happening, Mi is converted to SI, SI is converted to SI of T. At the receiver, this entire thing is nothing but the receiver. The receiver has to do reverse operation. Okay, so what reverse operation? From the received signal, it has to give the vector. From the vector, it has to estimate the signal Mi of T. Okay, so this estimation should be done at this point. Okay, and as I've already mentioned, using the likelihood function will be taking the decision in the sense, okay, for the received vector X or for the transmitted Mi, okay, whether the transmitted bit is M1 or M2 or MM, okay, that will be estimated at this point. Okay, to estimate this, I need X. And this X is derived from X of T. X of T is obtained from SI of T. Okay, so this is how the communication process will happen. So I'll just teach you in detail step by step. Okay, so here what we need to do, estimation of known signals in additive white Gaussian noise. So Xj, whatever I've got is a additive white Gaussian noise only, because additive white Gaussian noise is getting added with Xi of T. So X of T is also this X is also having that additive white Gaussian noise. So I need to estimate the known signal from this X. Okay, so the same block diagram, this block diagram only I'll explain you once again. So in the step 1, what we'll do, we'll have the message source, same repetition only. This is whatever I'm saying, it is just the repetition, but I'll give you a little clear outputs. Okay, so I'll have the message source. This is not the actual topic, it is just the introduction. Okay, just the introduction. Okay, introduction to this estimation of known signals in the additive white Gaussian noise, or it is also said to be detection of known signals in additive white Gaussian noise. Okay, both are same only. Okay, so you'll have the message source. Okay, you'll have the message source. Each message source will give m symbols or m messages represented as mi is equal to m1, m2, so on mm. Okay, and in the transmitter only, what we'll do, we will change this m1 to si of 1. That is what the representation here, right? So mi will be converted to si of t. So the transmitter, what it will do, it will convert m1 to s1 of t, or m2 to s2 of t, or m3 to s3 of t, so on m2 sm of t. Okay, so all this corresponds to si of t, and each one will be of duration from 0 to t seconds. Okay, or each one will be of t seconds. Okay, each one will be of t seconds. Okay, now what will happen, this si of t is transmitted through the channel. This si of t is transmitted through the channel. So in step 2, what happens? Step 1 is nothing but the transmitter part. Step 2, channel. Okay, what will happen? This si of t will get added with white Gaussian noise in the channel, and it will give you x of t, where x of t is nothing but si of t plus w of t. Okay, where x of t is nothing but the sample received signal, and w of t is nothing but the white Gaussian noise. Okay, so this is what will happen in the channel. Okay, coming to the receiver. Okay, receiver part is step 3. Okay, so what will happen here? So x of t will be received. Okay, that will be given to the receiver. Okay, and this receiver, as we have seen already, it will consist of bank of correlators. Where is that? Let me show you that diagram also. Bank of correlators. Product and integrator is said to be the correlator, right? So these are said to be the bank of correlators. Bank of n correlators. So this x of t will be given to this bank of n correlators, so that the same process I am repeating, that's it. Receiver with bank of n correlators. Okay, so what will happen? I'll get x. Okay, x vector will be obtained. Okay, so if you want me to draw, I'll just draw the which one I have shown you there. I'll just redraw it. It will give x of t will be taken. It will be passed through this correlator, so that I'll get x1. In the same way, it will get multiplied with phi 2 of t, and then integrate it from 0 to t dt, so that I'll get x2. In the same way, I will so on. Phi n of t, x of t will get multiplied with phi n of t, and then integrate it from 0 to t dt, so that I'll get xn. Okay, so these are said to be the bank of correlators. Each product and integrator is said to be correlator. Bank of correlators. Okay, so that we'll get the vector x, which is given by x1, x2, so on xn. Okay, we'll get x2, x1, x2, so on xn. Okay, so this is what we are going to get at the receiver end. Okay, just after the detector, this is what we are going to get. Okay, so and here what we need to do, X is not our final destination. We have to find out M cap. We need to estimate M cap. Okay, where this M cap should be equal to Mi. M cap should be equal to Mi. Okay, in order to do this, we'll have the decision rule. Okay, decision rule. The next step is nothing but the decision rule in the correlation receiver. Decision rule in the receiver. Okay, because if you observe the receiver, what is happening? From the x of t, we are getting x. Okay, based on this x, this vector decoder, it has to identify whether the received bit is correctly received or not. It has to make the estimate of transmitted one. Okay, that estimate should be equal to mi. Okay, so here the vector decoder, it has to take the decision with respect to the symbol that is transmitted. Okay, so if I want to get correct correct estimate, okay, if estimated value m cap, if estimated value m cap should be equal to mi, then the probability of correct correct decision. Okay, correct decision in the sense, see here from x, it has to estimate m cap. Okay, so whether whatever m cap I've got, if I want to say that it is estimated properly, then the correct probability, the correct probability to give the correct estimated value is given by PC, probability of here again it is conditional probability, because X is received, right? So X is received, from X only I'm just determining the M cap. Okay, so the probability of getting the correct correct decision is given by PC. PC indicates the conditional probability of average conditional probability of correct decision. Okay, so PC is nothing but average probability of correct decision. Average probability of correct decision, that is given by probability of M cap. M cap, instead of M cap I'll write as Mi sent, X received. Mi sent, okay, and X is received. Okay, so if Mi is sent and X is received, then we can find the average probability of correct decision by using the probability function as PC is equal to probability of Mi sent, X received. Okay, so this is the average probability of correct decision. Okay, so if I want to find the wrong decision, then probability of error I need to find. Wrong decision, it means that I need to find average probability of error. Okay, average probability of symbol error. Okay, maybe I have transmitted M1, but I would have got M cap as not M1, but something else like M something like that. Okay, M. Okay, some are M2. Okay, M1 is transmitted, but I'm getting M2. Okay, so this indicates that the received bit is not correct. Okay, so in order to find the probability of average probability of symbol error, I can just take as PE is equal to 1 minus PC. This is the correct probability of correct decision. Okay, this is the error in the decision. Okay, symbol error in the decision. Okay, so that can be given as PE is equal to 1 minus PC. Generally, PE plus PC should be equal to 1. Okay, since PE plus PC should be equal to 1, we can kind of find PE is equal to 1 minus PC. Okay, so that is what it indicates. Okay, so let me write the equation for this is nothing but average. AVG indicates average probability of symbol error. Okay, so I'll just come back again. Decision rule. Okay, so I'll get vector x. Okay, from the detector I'll get vector x. Okay, based on this vector x, I have to identify whether my m cap is nothing but the estimated output. So whether this estimated output is the correct one, whatever is transmitted at the transmitter end or not. Okay, so if I want to have the correct decision, then the probability of correct decision, average probability of correct decision is given by P, where Mi is sent and X is received. Mi is sent at the transmitter and Mi is sent, and at the transmitter end Mi is sent. Okay, at the receiver end X is received. Okay, so the average probability of correct decision can be represented as PC, probability PC, which is given by P. Mi is sent and X is received. Okay, so this is the conditional probability because there is a condition. Mi is sent and X is received. Okay, so since there is a condition, it is said to be the conditional probability. So we have got the average conditional probability of correct decision as P of Mi sent and X received. Let us consider I need to find the error probability. Symbol error probability. It means that Mi is sent, but okay, I'll just take as M1. M1 is sent, but estimated value M cap is not M1. Okay, so not M1 indicates it is the error. Okay, so if I want to find the average probability of symbol error, then the equation is P is equal to 1 minus PC, because you know that the total probability should be equal to 1. Okay, so P is equal to 1 minus PC. So in terms of equation, P will be equal to 1 minus probability of Mi sent, X received. Okay, so this is the probability of error. Okay, so if I want to get the correct probability, okay, correct output, if the estimated value, whatever I'm estimating, if the estimated value is to be correct, okay, then what how should be your PE should be more or less. PE should be more or less. If estimated value M cap is correct. Okay, correct in the sense if M cap should be equal to Mi, I am asking you people how should be this PE. PE should be more or less. Have you understood my question? Have you understood my question? Are you all there? Prajwal?
Yes, ma'am.
So have you understood my question? Tell me yes or no. If you have not understood the question, I'll ask again.
No, ma'am.
Okay. So here, based on X, the detector encoder. Okay, the detector vector encoder. What it has to do? It has to give us the estimate M cap. Okay, so here I'm talking. Okay, so whatever I'm transmitting, you will have the decision making device at the receiver end, which will estimate whatever I'm speaking is the same or not. Okay, so that that will be given by the decision rule. What is that? Vector decoder. Okay, vector decoder will check some decision rule, in the sense it will check from some value. Okay, so it will check the threshold value. Okay, some threshold value will be there and it will check that value and it will decide whether whatever I have based on the received parameters, it will compare with the threshold value, and what it will do, it will give the decision whether M1 is transmitted or M2 is transmitted or M3 is transmitted. Like that, it will make the decision. Okay, so this decision rule, I'm just trying to find how the decision will be done. Okay, so probability. So I'm just taking the probability because I cannot say exactly it will be done. Okay, so for that reason I'm using the probability here. Okay, so probability of correct decision. Okay, probability of correct decision in the sense M cap is sent and MI is received. Okay, so MI is sent and M cap is received, and this M cap is nothing but your MI. Okay, in order to find the correct probability, I am taking PC. Okay, PC is equal to probability of MI is sent and X is received, because here the decision is made with respect to the X only. Okay, so MI is sent and X is received. Okay, so this is the correct probability. Now I need to find the error probability. Okay, error probability, symbol error probability. Okay, symbol error probability in the sense M1 is sent but M1 is not received. M cap is not equal to M1. Okay, so that indicates the error probability. So here again I need to find the error probability. You know that the correct probability plus the error probability will be equal to 1. Always the total probability will be equal to 1. Okay, so if I want the error probability, I can take as P is equal to 1 minus PC. Okay, so 1 minus PC. You already know the equation for PC. Okay, PC is nothing but P MI sent and X received. Okay, so from that I have written the equation for P. Okay, so now my question is, if M1 is transmitted and if I want my M cap is equal to M1 only, how should be your PE? PE should be more or less? P is more indicates what? P is less indicates what? P is more indicates the error probability is more. Error probability is more in the sense whatever I have received is not right. Right. So P is less indicates that P is less indicates that the error probability is less. If error probability is less, then whatever M cap I've received will be M1. Okay, that is what it indicates. Okay, so in order to make the proper decision, the probability of average probability of error, PE should be minimized. PE should be minimized. Whereas PC is nothing but the correct probability. PE should be minimized and PC should be maximized. If PC is probability of detecting correct error, taking the correct decision is increased, it means that maximized. It means that there is no error. Okay, so here we need to design the receiver in such a way that the probability of error will be minimized and the probability of correct decision will be maximized. Is it clear? Is this clear why PE should be minimized and PC should be maximized? PC indicates correct decision. Correct decision should be more. Okay, if the correct decision is more, then it means that the receiver, whatever is designed, is optimal. Optimal in the sense it is giving you the right value. Or I can reiterate the same thing as PE. PE should be minimized. PE in the sense probability of error. Error is minimized. Error is minimized in the sense the estimate, whatever you are estimating from the receiver, it is the correct one. Okay, so I need to design the receiver in such a way that the probability of error is average probability of error is minimized and the average probability of making correct decision is maximized. Okay, this is all related to the estimate of estimation of your signals, known signals from the additive white Gaussian noise. So I still didn't go to the topic. This is what only the introduction. Okay, hope when I go to the topic you'll get the clear clarity. I don't know, but I'm trying to like make you understand. Hope this is clear to all of you. The class is done for the day. If you don't have any doubts, you can leave, or else you can stay back and ask me any kind of doubts. Any kind of doubts. Otherwise, the class is done for the day. I'll pass the notes to you people. Just go through it today only. Okay, so that next classes will be easy for you. Okay.
Thank you, ma'am.
Thank you, ma. Thank you.
Thank you, ma'am.
Thank you, ma.
Thank you, ma'am.
Thank you, ma. Anybody has got any doubts? Bhavna? Kavya? Kavya is there? Kavya?
She left, I think so, ma'am.
Okay, okay. Bhavna?
Yes, ma'am.
Are you understanding? Shreya?
Yes, ma'am.
Are you understanding, ma?
Yes, ma'am.
Okay.
Ma'am, can we leave?
Yeah. You can leave. You can leave. If you don't have any doubts, you can leave.
Okay.
Bhavna? Bhavna, are you there? All of you can leave. ఆన్ చేసిపోయింది వాళ్ళు